Now we're going to look at the required practical, which is measuring the EMF of an electrochemical cell. So we're going to look at connecting a Cu2 plus Cu half cell with a Zn2 plus Zn half cell. So what we do is, firstly, we clean a piece of copper and a piece of zinc with sandpaper. And we do this so that we get rid of all the impurities on the surface of them. We then use some propanone and cotton wool to wipe the surfaces of them to degrease them. We place the copper rod into an 100 centimeters cubed beaker with about 50 centimeters cubed of copper sulfate solution. And it's very important that we put the copper metal into a solution with its own ions, so with the Cu2 plus ions. And we do the same with the zinc. So the zinc metal goes into a 50 centimeters cubed of zinc sulfate. So it has the zinc 2 plus ions in the solution. And then what we do is we lightly plug one end of the salt bridge with cotton wool and fill it up with the solution of sodium chloride. In this case, the salt bridge we're using is an upside down tube. And then we plug the free end of the tube with cotton wool, which has been soaked in sodium chloride. And this is how we join the two beakers so that the plugged ends are in the separate beakers. We then connect the two pieces of metal using crocodile clips and wires, and we connect them up to a voltmeter so that we can measure the EMF later. So what happens is that the electrons will move, and this creates the EMF. And so now we can have a look to see what actually happens. So we know that the electrons move from the half cell with the most negative standard electrode potential to the one with the less negative standard electrode potential because it's a better reducing agent. And so we can look at this table and we can see that we have zinc and we have copper. And so because zinc has a more negative standard electrode potential, it loses electrons easily, So because zinc has a more negative standard electrode potential, it loses electrons more easily, and so it is the better reducing agent, and therefore the electrons will move from the zinc half cell to the copper half cell. And so we have electron flow this way. If we were to write out the standard cell representation, then we would have the zinc on the left because that's the one which is being oxidized. So we'd have zinc the solid and then a solid line to indicate we're changing phases. So we've got aqueous, and then this is the salt bridge. And then we have the Cu2 plus ion, and then copper the solid. And so because we've now worked out how the electrons flow, we can work out what actually goes on in both of the half cells. So if zinc, the metal, is losing electrons, then that means that Zn2 plus ions are formed. So we write this as Zn goes to form Zn2 plus 2 electrons. And for the copper half cell, because it's gaining electrons, that means that the copper 2 plus ions are being reduced. So we have that the Cu2 plus ions are gaining 2 electrons each to form copper. We can then record the EMF, and we already know how where this EMF should kind of lie because of the equation that the EMF is equal to the standard electrode potential of the right-hand cell minus the standard electrode potential of the left-hand cell. And so we know that for this experiment, we should have an EMF of approximately 0.34 minus 0.76, which equals plus 1.1 volts. So in our experiment, we should expect to get around this figure. Now we're going to have a look at some questions. So for the first question, for the following, draw the conventional cell representations and calculate the cell EMFs. So for A, we know that the half cell with the more negative standard electrode potential is the one which goes on the left. And so this must be the chromium half cell. And then we have to decide between what to put first. Do we put the chromium or the chromium 2+ ion? Well, the rule is that the more oxidized version of it goes in the middle. So the more oxidized version is the one with the higher oxidation number, and that goes in the middle. So that means that the one with the lower oxidation number goes on the outside, and this is the chromium because the oxidation number of chromium is 0, and the oxidation number of chromium 2+, the ion, is +2. So we have chromium, and you've got to remember to write the state it's in as well, so it's a solid. And then we write the Cr2+ aqueous ion, and because this is aqueous and the chromium is solid, we have to draw a solid line to separate between phases. So then we have the Cr2+ aqueous ion, and then we draw the salt bridge, which is a double line. And then we do the same with zinc. So we think which one is more oxidized? Well, the one with the bigger oxidation number, and this is Zn2+, so that goes in the middle. So we have zinc 2+ ion, which is aqueous, and then another solid line to separate between aqueous and solid, and then we have zinc the solid. And the way we work out the EMF is if we do EMF equals the standard electrode potential of the right minus the standard electrode potential of the left. And so in this case, the EMF must be equal to minus 0.76 minus 0.91. And so we get plus 0.15 volts as the EMF. And just a quick note that the EMFs should always be positive. So if you've got a negative value for the voltage, then you have done something wrong. For B, we do the same thing. So we think, firstly, which one has the more negative standard electrode potential, and that is the copper. So the copper half cell goes on the left. And now we think which one out of copper and copper 2+ ion is the most oxidized, and that goes in the middle. And so that means that the copper goes on the outside. So we have copper solid, and then that's separated by a straight line, and then we have copper 2+ the ion, and then we have the salt bridge, and then now we pick between the Fe3+ and the Fe2+. So again, we think which one is more oxidized, and that is Fe3+ because the oxidation state is higher than for Fe2+, because the oxidation state for Fe3+ is +3, whilst the oxidation state for Fe2+ is +2. So Fe3+ goes in the middle, and it's aqueous. So because Fe3+ and Fe2+ are both aqueous, that means that we use a comma instead of a solid line to separate them. So we have a comma, and then we have the Fe2+. And also because they're both aqueous, we don't have a solid electrode, and so that means we need to use platinum. So now we draw the straight line because the platinum will be solid. So the platinum always goes on the outside no matter what. And this is our cell representation. So to work out the EMF again, we take away the standard electrode potential of the left from the right. So we would do 0.77 minus 0.34, and that equals plus 0.43 volts. And then for C, firstly we work out which one has the more negative standard electrode potential, and that is the chlorine half cell. And then now we think about which one is more oxidized, so that would be the chlorine, so the Cl- would go on the outside. However, because chlorine is a gas and the chloride ion is an aqueous species, that means that we need another solid again, and so we go to platinum. So platinum goes on the outside, as always. And then now we can write in the chloride ion and the chlorine molecule. So first we have the chloride ion, which is aqueous. And now we have another line because the chlorine is a gas, it's not aqueous. And then we have the salt bridge. And now we have the MnO4 minus or the Mn2 plus or the H plus to choose from. And so what we do is we work out the oxidation states. So for MnO4 minus, we have -2 here. So if you times that by 4, you get -8. And we have x minus 8 equals -1. So x equals +7. If you don't remember how to work out oxidation states, then you should quickly just go onto the video about oxidation states and then come back. So the oxidation state of manganese is +7, and then the H plus is +1, and then the manganese ion 2 plus is +2. So that means that the most oxidized one goes in the middle. So that means that the MnO4 minus will go in the middle because the oxidation state is the biggest. So we have MnO4 minus, and this is aqueous. And then we add in the Mn2 plus because it has a lower oxidation state or oxidation number, and it's separated by a comma because they're both aqueous. And then we also add in the H plus, and this is also separated by a comma because it's also aqueous. And now again we need a solid, so we use platinum. So the EMF for this cell would be equal to 1.51 minus 1.36, which equals plus 0.15 volts. So before I move on to question 2, feel free to click off the video and try it for yourself first. So it asks us, would the electric potential for this half equation change if we used all these different conditions? So the first thing we should spot is that this half equation is actually the half equation for the standard hydrogen electrode. So the normal conditions for the standard hydrogen electrode are that the pressure is 100 kilopascals, or that's equal to 1 atmosphere. The temperature is 298 Kelvin, and also the concentration of H plus ions is 1.00 moles per decimeters cubed. And those are really important facts to remember about the standard hydrogen electrode, and also that the EMF we set as 0. So now let's have a look at the questions. So for A, what would happen if we increased the pressure from 100 kilopascals to 200 kilopascals? So if we look back to the equation and see how many moles of gas we have on each side of the equation, so on the left we have 0, and on the right we have 1. And so what this means is that if we have increased the pressure, that means that the equilibrium shifts to decrease the pressure, and so favours the side with the least amount of gas moles. So in this case, it would be the left. So it would favour the back reaction. So the equilibrium would shift to the left. So the number of electrons present will increase. Because the number of electrons has increased, that means that the electric potential of it will be less than 0.00 volts because it will become the negative. So for A, the answer is it'll become less than 0.00 volts, and that's because if we increase the pressure, then the equilibrium shifts to the left, and so we have more of the reactants, so more electrons. For B, if we use a piece of platinum with a greater surface area, this actually doesn't do anything because a greater surface area increases the rate of reaction, but it'll increase the rate of reaction of the forward and the backward by the same amount, and so they cancel out, so nothing happens. For C, if we use sulfuric acid with a concentration of 0.5 moles per decimeters cubed, well, because a sulfuric acid has two atoms of hydrogen, that means that actually the concentration of H plus ions in H2SO4 is 1 because there's 2 of them. And so there'll be no effect on the EMF. So for D, if we use hydrochloric acid with a concentration of 0.5 moles per decimeters cubed, well, if we look back at the equation, and if we have now got less, the concentration of H plus ions is smaller, that means that the equilibrium will produce more of the H plus ions, and so it favors the back reaction, and so the equilibrium shifts to the left, so the potential would also be less than 0.00 volts. So got less than 0.0 volts. So the reason is because if we decrease the concentration, then the equilibrium shifts to the left. And so we have more electrons produced. And then for E, if we use a temperature of 50 degrees instead, also the EMF will decrease to less than 0.00 volts, and that's because increasing the temperature will shift the equilibrium to the left, and we can see that from the equation because the enthalpy change is negative, which means the forward reaction is exothermic. So if we increase the temperature, then it will favour the back reaction, the endothermic reaction, and so more electrons are produced, so the EMF will be less than 0.00 volts again. So we have that it's less than 0.00 volts, and if we increase the temperature, then the equilibrium shifts to the left and more electrons are produced. And also it's useful to remember that the conversion between degrees Celsius and Kelvin is 273. So if you want to go from degrees to Kelvin, then you'd have to add on 273. Hi everyone, thank you so much for clicking onto the video. We're going to look at some harder questions for electrochemical cells. So it says to use the table below to answer the questions. For A, select the species which is the most powerful reducing agent. So the meaning of reducing agent is something that loses electrons. So it's an electron donor. Because the thing that's being reduced gains electrons, and so reducing agent is an electron donor. And first of all, what we think is a half cell that has a more negative standard electrode potential a better have a better reducing agent than the more positive standard electrode potential, or is it the other way around? And well, when we connect up two half cells, the half cell with the most negative standard electrode potential, electrons will come from there to the more positive one. And so there's our answer. So that means that we're looking at this zinc half cell at the top because it's the most negative. So that means it gives its electrons more easily. And so there's a better reducing agent in that half cell. And now we have to choose between Zn2 plus or the zinc. And now we think which one is actually losing the electrons and which one is gaining the electrons. And so zinc has to gain electrons to form Zn, like this equation here. But however, zinc has to lose electrons to form Zn2+, and that means that the reducing agent in this half cell is the zinc, because we have the half equation zinc goes to form Zn2+ plus 2 electrons. So these 2 electrons here are getting donated to the thing that it's reducing, so the other half cell. And so our most powerful reducing agent is zinc. And then for B, select a species which an acidic solution will reduce VO2 plus to VO2 plus, but will not reduce VO2 plus to V3 plus. First of all, the in acidic solution bit just means that there are H plus ions. And so if we want something that will reduce VO2 plus to VO2 plus, we need a half cell with a more negative standard electrode potential. And if we want something that doesn't reduce VO2 plus to V3 plus, then we need a half cell with a standard electrode potential which is more positive than this half cell. And so if we find these two equations, so we've got this equation here and this equation. So this is the equation they number first. So I'm going to call that number 1. So that's going to be number 1. And then this is going to be equation 2, just as they've listed it. And so we need a half cell which is more negative than equation 1, but less negative than equation 2. So that means that the species is in this Fe3 plus Fe2 plus half cell, because it can reduce equation 1 but not equation 2, because it's in the middle. The standard electrode potential is in the middle. And so now we pick one of the equations. So I'm going to look at the first equation. So the standard electrode potential, which is underneath the Fe3 plus Fe2 plus. Now that one is being reduced. So that means that the VO2 plus ion is gaining the electrons, like how they've written it in this equation. So that's what's happening. So we must have this equation but reversed, because electrons need to be given to the VO2 plus half cell from the Fe2 plus Fe3 plus. So that means that Fe2 plus is going to be forming Fe3 plus and the electrons. And so the answer of the species that will reduce the VO2 plus to VO2 plus but will not reduce VO2 plus to V3 plus is Fe2 plus. We can always check this with the other equation as well. So with the other equation, what's happening is that it's being oxidized because it's not being reduced. So the reverse of equation 2 is happening because it's giving away its electrons. And so that means that the Fe3 plus is accepting the electrons. So the species that will not reduce the V2 plus to V3 plus is still the Fe2 plus. So that is our answer. For C, select a species which in acidic solution will oxidize VO2 plus to VO2 plus. So to oxidize something, we need that half cell to have a more positive standard electrode potential. And so the more positive one is in here. So now we know that it's in this chlorine chloride half cell. So now we need to work out between chlorine and chloride which one is the oxidizing agent. And so the oxidizing agent is the electron acceptor. And so from this equation, we can see that chlorine is the electron acceptor because we're adding on 2 electrons to form chloride ions. And so our answer is chlorine. So before I move on to question 2, feel free to pause the video and try it for yourself first. Use the standard electrode potential data given in the table below to answer the questions which follow. For A, an excess of potassium manganate was added to a solution containing V2 plus ions. Determine the vanadium species present in the solution at the end of this reaction, and state the oxidation state of vanadium in this species and write a half equation for its formation from V2 plus. Okay, so if we add more potassium manganates, that means we're adding more MnO4 minus ions. And so we can see in this equation here that we would have more of these MnO4 minus ions. And so if we have this connected up to this V2 plus here, if we have these two half cells connected up, because the V2 plus V3 plus half cell has a more negative standard electrode potential, this minus 0.26 compared to this 1.52, that means that the V2 plus V3 plus half cell would reduce the MnO4 minus Mn2 plus half cell. And so what happens is that because the V2 plus V3 plus half cell reduces, that means that it gives out the electrons. And so the equation that's happening is that V2 plus is being turned into V3 plus the electrons. So these electrons are now transferred to this to the MnO4 minus to produce this Mn2 plus. And so if we have an excess of potassium manganate, first of all, the V2 plus will turn into V3 plus. And then if we look further at the equations, we have a V3 plus here. And if we add this with water, then we form VO2 plus. And because this manganate produces water in this reaction, this water then reacts with the V3 plus that we formed here. And so what happens is that the V3 plus then turns into VO2 plus ions. And then again, this VO2 plus added with water, it then forms as VO2 plus. So if we've got the excess of potassium manganate, more and more water is formed. And so this VO2 plus will then turn into VO2 plus. And of course, this is also because all of these equations with the vanadium, they all have a more negative standard electrode potential, so that they always act as the reducing agent. And so that's why eventually the V2 plus will turn into this VO2 plus. So for A, determine the vanadium species present at the end, that would be the VO2 plus. And now we need to state the oxidation state of it. So if you don't remember how to find the oxidation state, then quickly go back to the redox videos and then come back. So we have the VO2 plus, and oxygen is nearly always -2, as we've learned as one of the rules. So we have -2, and then we have 2 of the oxygens, so we have another -2. And then we have x -2 equals +1, because +1 is the overall charge. And so x is equal to +3. So the oxidation state of vanadium must be +3. And now write a half equation for its formation from V2 plus. So again, if you can't remember how to write half equations, quickly go back to the redox videos and then come back. So we have V2 plus, and that's going to form VO2 plus. And so I'm just going to do this quickly. So we'll balance the vanadiums, that's already done, then balance the oxygens. So we've got 2 waters, and then we have 4 H pluses, and then this charge is +5, and this charge is +2. So that means we need 3 electrons on this side. And now it should be balanced. And then for B, the cell represented below was set up under standard conditions. Calculate the EMF of this cell and state with an explanation how this EMF will change if the concentration of Fe3 plus ions is increased. So here we have the H2SO3 cell, so this one, and then the Fe3 plus Fe2 plus. So again, because the H2SO3 half cell has a more negative standard electric potential. That's the one which will be reducing the Fe3 plus Fe2 plus. So that means that to find out the EMF, what we do is that we do the standard electric potential of the right minus the standard electric potential of the left. And this comes out to be 0.77 minus 0.17, and that equals plus 0.60 volts. And then we're asked how this EMF will change if the concentration of Fe3 plus ions is increased. And so what happens is that when, so firstly, the H2SO3 and SO42 minus half cell is reducing the Fe3 plus Fe2 plus. So it's reducing the Fe3 plus ion by giving it an electron to form the Fe2 plus ion. And so if we increase the concentration of Fe3 plus, that means there are more of them to accept electrons. And so they accept more and more electrons, and that makes its standard electric potential even more positive. And so what that does is that if we look at this equation here, so we have EMF is the standard electric potential of the right minus the standard electric potential of the left. If this is now bigger and this has remained the same, then that means that the overall EMF of the cell will increase because there are more of the Fe3 plus ions to accept loads and loads of electrons, so its standard electric potential is bigger.